Hi to everyone, and welcome to my thesis dissertation. The topic is time series anomaly detection for large-scale computing infrastructure, like, for example, at CERN, where I spent my internship and I wrote this thesis. Let's start with a brief of context. Why is time series anomaly detection important, and in particular, why is it at CERN? So CERN is the largest particle physics laboratory in the world, and they have several experiments, and each of those experiments involves millions, if not billions, Swiss franc investments. Therefore, every step in those experiments is of crucial importance. Also, the elaborations of results, and these elaborations happens in the data center, where data becomes knowledge as it is written on the facade of the data center. To give you a further insight into the infrastructure and the challenge that this problem poses, the CERN private cloud includes more than 7,000 server machines, and each of those server machines is monitored with up to 170 metrics, so time series metrics. We understand that this complexity needs to be monitored and needs to be reliably monitored, as I said, and we want to reliably detect anomalies. So this is the need. So we need an anomaly detection system that does this for us. On this line, the goal of this work is twofold. We have first, as we said, to find a way to spot anomalies in the data center computing infrastructure in a reliable way. And for that, we compare 10 methods. So we run an evaluation, individual methods, and also ensemble strategies, 6 of them. In order to have this evaluation study, we needed to have a benchmark data set. And because of that, we had to collect it. It was not there at the beginning. Therefore, we put in place also a system that not only predict anomalies using the algorithms, but also helps the experts to collect data sets, benchmark data sets. So let's start with this system. So the overall anomaly detection system is one of the contributions that led us to the creation of a data set. And this was possible because we designed a workflow that facilitated the annotation of data to the CERN expert. And this let us create, with this anomaly detection system, it let us create 2 data sets, 2 novel data sets for the anomaly detection use case. Let's now move into the 2 parts of this system. So we have the data analytics core, in which we produce the results that the expert will be able to see in terms of anomalies. So here we start from the data source, the servers, we prepare them, we preprocess, create a card encoding for the unsupervised anomaly detection methods that includes 2 families, the traditional anomaly detection methods and the deep learning ones. Once we have these individual methods, we want them to combine them in order to hopefully get a better detection performance, and with ensemble strategy, we will then send those anomalies to the monitoring dashboard where the expert can see them. And independently from this chunk, we will have the annotation pipeline. The annotation pipeline is where the expert can inspect through the monitoring infrastructure the time series and annotate intervals onto them. And this was facilitated by a work done in this thesis. We were able then to collect 2 benchmark data sets that, as the name says, they were used to give a qualitative evaluation of the performance of the methods, both individual and ensemble strategies. This overall system was done with fully open source technologies. We used from HDFS to Spark, the core was done in Python, and we used TensorFlow as deep learning libraries. And then we use Docker to containerize all the steps in an independent way. And we use a bunch of other components like a logging system and a temporary storage system to send results to the monitoring infrastructure. That's the one in use at CERN was and is Grafana. And all the tasks in this system were orchestrated thanks to Airflow, Apache Airflow. Let's now go into the core, so those algorithms. Now that we move into the algorithmic perspective, as we said, we have benchmarked 10 methods, and we benchmark both existing methods that were adapted to work for our particular problem formulation, but also novel variations. We group them in the traditional methods, the deep learning methods, and also the ensemble strategies. We will go into the details in the next slide. In terms of problem formulation, every algorithm is modeling a scoring function for our anomaly detection problem. And a scoring function is a function from an entity, a multidimensional data point, to a real value. And this real value indicates the degree of anomalousness, as you can see. And our entities, in our case, are servers. We would then have the temporal dimension. So we're not only scoring entities, but we are scoring entities throughout time. So as the time series you can see here, throughout time, we are repeating our analysis in windows of 8 hours. And each window is containing, as I said, 8 hours, and we repeat this analysis every 8 hours. So the input data for our anomaly detection algorithm is a window representing our entity throughout time. So one window represents 8 hours, and in particular, we got 11 metrics for every window. And the metrics are like CPU load, memory, and swap space. And for the window, we devised 2 different encodings, the image-like encoding and the vectorized one. They have different advantages. The first one, the image-like, let us to encode in the temporal dimension in the X direction, while on the Y direction, we have the M matrices. Then the fact that it's an image will let us to use convolutional neural networks. The vectorized representation, on the other hand, enables us to use the database outlier detection literature method with a vectorized representation. This vectorized representation is created by concatenating the rows of the image representation. So we have the first metric, the second metric, and so on. Let's now dive deeper into the methods. Let's start with the novel one, the one that we proposed. So here we have a forecasting convolutional neural network. The principle here is based on the forecasting objective. It means that we train this model to forecast the next time step. And based on the error that our models does in the prediction, we will create our anomaly score. And this error is computing at each step of the window that we can see at the input, at the test time. We then use the errors that we do in all the steps, and we create the final anomaly score. The same principle applies to a similar method. In concept, we still use the forecasting principle, but with a vector autoregressive model that is traditional from time series models. And here we use a shorter history, and the difference here is that we do not learn a model for all the servers, as it happened in a convolutional neural network, but we learn a model on a specific server, and we select a group of them at random, like 20, to represent also the broader group of servers. And this is done because the model is less flexible, and we wanted to use the convolutional neural network to do that in the previous step. And here it's not possible, so we applied this step. Then we have another family, the one based on reconstruction error, the family of autoencoders. We have fully connected methods, convolutional autoencoders, and also LSTM-based one. The LSTM-based one includes also the representation of the temporal sequence. In terms of traditional methods, we have selected the 5 of them. The one that I want to mention is the principal component analysis method that is used also in other setting in machine learning, and also the isolation forest that is one of the most recent among the one in this group. Once we have the prediction of the single methods, we have here 10 predictions for the 10 methods that I just described you. We want to enable ensemble strategies. So we want to put them all together in order to create a new score that is derived from the single ones. And among the various unsupervised techniques that we explored that were suggested in the literature, like taking the average, taking the maximum, we also explored this novel variation that is a weighted sum of the anomaly score of the single methods, where the coefficients of this weighted sum are learned through linear regression. And this linear regression model is learned by using the first part of the dataset, so the very first days of our benchmark dataset. The experimental setting, the CERN infrastructure is large. The servers are more than 7,000, but they have some regularities. They are grouped, and these groups contains 100 to 200 servers, and each of those groups has a homogeneous characteristic. So it means they have the same hardware setup, same software configuration, and also target usage. Based on the target usage, we decided to create two different data sets, the batch dataset and the shared dataset, representing two different use cases. So we have for the batch dataset, we have that all the machines in this group are having similar workloads, and these workloads are the elaboration of the data from the experiments. While the other use case is the shared use case, where each machine is used by a different service or different user at CERN. So you understand that those are mostly independent jobs and they don't have the same regularity of the batch use case. In terms of figure of merits, we decided to adopt the threshold independent method. So we draw the distribution of the anomaly score of the different methods, and then we slided the threshold, computing the different metrics, true positive rate and false positive rate, and creating the receiving operative curve, where each threshold corresponds to a point on this curve, and if we slide the threshold, we create also the other points. By using the area under this curve, we use a single value matrix to evaluate our algorithm and compare them among each other. So the experimental results section tells us for the first use case, the batch, that we have overall good performance from both the traditional and deep learning methods. So we have two traditional methods that are in the top three, but overall there is not that much difference between the deep learning and traditional one. Therefore, we might prefer to use the more simpler traditional method, like PCA or isolation forest. Another point with PCA, we compared it with the closest deep learning methods, that is the autoencoder, and we realized that they are getting a similar performance. And if we dive a bit more deeper, and we saw that they have also similar anomaly score for both normal and anomalous instances. Therefore, we should prefer linear techniques like PCA because they are simpler and they seem to be enough for this use case. If we compare to the other use case, the shared, we first see if we're putting one next to the other, we see that the shared one are achieving a significant lower score. And this is a generalized behavior of all the methods. And so this confirms our intuition that this setting is more difficult. And in this more complex scenario, the deep learning methods are 2 out of 3 in the top 3. So then here we might motivate the use of methods like such as LSTM for this more complex scenario. A consideration in terms of the methods one of the methods that we propose, the forecasting convolutional neural network, we have that it is getting the same result of another reconstruction approach, autoencoder, similar performance, as we can see from the histogram, and also similar anomaly score. But the difference here is that our method has an edge in terms of total parameters. It's a simpler model with less parameters. In terms of ensemble results, then we want to explore different techniques. As I said, there is the maximum and the averaging that are suggested in the literature, and they are confirming to be, on average, showing a good performance, not being biased by the worst method. As you can see here, they are still robust to the presence of quite worse method. On the other side, the consideration about our method, the linear regression based one, we can see that it has a slightly higher result than the other unsupervised techniques, because of course we are using also supervised information. The difference is not significant at all, so it might be an indicator of that it's worth exploring, but at the moment it's not clear. In terms, to summarize experimental result, we have that in terms of task difficulties, we have the batch scenario that is easier and it's possible to tackle it with linear methods. And on considerations about the modeling, we have that whenever we include the temporal dimension in our encoding, we can either get more parsimonious model, for example, the forecasting CNN, or even a more performant model like the autoencoder LSTM. So the product of the thesis, to summarize again, we have an annotation system that we use to collect the data set, the 2 data sets, and finally the overall anomaly detection system, including all the methods. And the one that I just summarized is the comparative evaluation study of the method. So to sum up, can we reliably spot anomalies in the CERN data center use case? The question is yes, partially. It depends on the use case, so the user category. So if we are in a batch case, PCA methods, traditional methods, and PCA in particular might be enough. While for the shared setting, we have a more challenging scenario where deep learning methods show an advantage to model this more complex problem. That's all. Thanks for the attention. I wish to thank CERN, Domenico, my CERN supervisor, my professor Boracchi from Politecnico, and the counterparts from TU Berlin. Thanks for the attention.